On the morning of April 12, 2016, in a room at the top of One World Trade Center, a Russian-born billionaire named Yuri Milner stood at a podium and announced that humanity was going to another star. Stephen Hawking was beside him. He spoke through his synthesizer, slowly the words arriving one at a time in the room. The gravity of Earth had once held humans down, he said. Now something was going to lift us off it, not toward the Moon or Mars or the outer planets, but toward Alpha Centauri, the nearest star system to our own, 4 light-years away. The initiative had a name, Breakthrough Starshot, and a budget of $100 million and a 20-year timeline. Mark Zuckerberg was on the advisory board. The physics had been worked out. The engineering, they said, was tractable. A fleet of gram-scale spacecraft, pushed by a ground-based laser array, would accelerate to 20% of the speed of light. That was 10 years ago. Hawking died in 2018. Milner has largely stepped back from public life. The $100 million has been mostly spent. The laser array has not been built. No prototype spacecraft has flown. The 2036 launch date announced from that podium has slipped into a future nobody names anymore. This is a video about the physics of reaching another star. It is also a video about a specific pattern, the way ambitious space concepts get announced in rooms full of famous people, generate a wave of press, and then quietly, over the course of a decade, stop being mentioned. Starshot is not the first instance of the pattern. It is probably not the last. It is worth understanding why the pattern happens, because it determines which of humanity's imagined futures actually get built. The nearest star system is 4.37 light-years from Earth. Nothing we have built is going there. Here is why. The obvious way to reach another star is a sail. Light exerts pressure. When a photon strikes a reflective surface, it transfers a small amount of momentum, 9 micronewtons per square meter, at Earth's distance from the Sun. This is a real force. It is small, but it is continuous, and unlike a rocket, it does not require the sail to carry any fuel. The concept was demonstrated in 2010 with IK-AROS. The Planetary Society followed with Light Sail 2. NASA attempted NEA Scout in 2022. Solar sails work. The physics is real, but solar sails have a problem. The sun becomes a weaker light source the farther you get. A sail that provides useful thrust near Earth provides essentially nothing by the outer solar system. They are not a mechanism for leaving it. Even the best concepts top out at a few hundred kilometers per second. At those speeds, Alpha Centauri is more than 6,000 years away. So the obvious answer isn't enough. Something has to replace the sun as the light source. Something like a laser. The idea of using a laser to push a light sail is older than Starshot by half a century. In 1962, physicist Robert Forward began publishing on the concept. He was a serious physicist who also wrote science fiction. He proposed antimatter propulsion, tethered satellites, and a laser-pushed light sail that could deliver a crewed spacecraft to another star and bring it back. Forward's proposals were enormous. He died in 2002 without seeing any of it built. What changed in the 2010s was miniaturization. A gram-scale spacecraft could carry cameras and sensors that would have required a full-size satellite in Forward's era. It needed a sail the size of a bedsheet, pushing a spacecraft the size of a postage stamp. The laser still had to be extraordinary, 100 gigawatts, but the total system shrunk from civilization scale to merely enormous. The insight was not that it had suddenly become easy, but that it had become tractable. The technical challenges fall into demonstrated things, actively worked on things, and things not yet started. What has been demonstrated? Solar sails work. Chip-scale spacecraft work. KickSat-2 successfully deployed over 100 gram-scale satellites in 2019. Small phase-locked laser arrays exist. What is being actively worked on? Sail materials with required optical properties. A 4-meter sail weighing a gram must reflect essentially all light. Any absorption turns into heat and vaporizes the sail. Researchers have published designs for reflective metamaterials. Small samples have been fabricated. None has been demonstrated at meter scale. It is being worked on. Chip-scale sensors are similarly being developed. What has not been started? The full laser array, 100 gigawatts, phase locked across a square kilometer. The largest demonstrated arrays are in the kilowatt range. The gap is 8 orders of magnitude. Every one of tens of millions of laser emitters must remain phase coherent while compensating for atmospheric turbulence. The pointing accuracy required is like holding a laser on a dinner plate 1,000 kilometers away. The energy budget has not been solved. 100 gigawatts for 10 minutes is 17 gigawatt hours, $1 million of electricity per shot, requiring infrastructure that does not exist. And the interstellar coast. During 22 years at 1/5 light speed, the spacecraft will collide with dust. A microgram grain at that velocity carries the kinetic energy of a rifle round. Estimates put a fully operational laser array in the range of $50 to $100 billion, comparable to the International Space Station. The question is whether humanity will spend it. The optimistic case for Starshot, the initial $100 million, was meant to validate the concept so national space agencies would step in. Philip Lubin argued the array has applications beyond propulsion. It could deflect asteroids or remove orbital debris. This is the dual-use infrastructure argument. Here's why it probably fails. 10 years later, no national agency has committed to the array. US, European, and Chinese planning documents did not prioritize interstellar precursors. Meanwhile, the scientific case is being eroded by telescopes like the Extremely Large Telescope, which will image Proxima Centauri b. By the time a Starshot mission could return data, astronomers will have accumulated decades of data from Earth-based telescopes. The dual-use pathway remains plausible in principle, but unfunded in practice. This is the pattern. Ambitious concepts, asteroid mining, orbital hotels, lunar extraction, have real physics, but no path to deployment. Starshot is the best of these because the physics remains valid. The follow-on funding does not arrive. The advocates age out. Starshot's failure to fly does not mean the physics was wrong. The physics is patient. The people ultimately decide if the array gets built. The follow-on funding does not arrive. The advocates age out. Starshot's failure to fly does not mean the physics was wrong. The physics is patient. The people ultimately decide if the array gets built. If interstellar travel happens, it will be through a serious precursor mission focused on the outer solar system, a small demonstrator that builds institutional muscle memory. None of these exist at scale right now. In the meantime, Forward, Hawking, and Dyson are dead. The generation from 2016 will not see if the mission flies. Somewhere, sail material is catching sunlight, moving slowly held aloft by photons. In the meantime, Forward, Hawking, and Dyson are dead. The generation from 2016 will not see if the mission flies. Somewhere, sail material is catching sunlight, moving slowly, held aloft by photons. The nearest stars remain points of light in the sky, 4 light-years away, close enough to see and much too far to reach. Whether that changes depends more on what we decide than on what we discover.